I'm very pleased to be here today and to be part of this eMonday. So as Mr. Metzger already introduced, I'm responsible Senior Manager Business Development for the energy markets, so energy management mainly. And this also includes the infrastructure market and the electric vehicle chargers. So today I want to talk or make you more familiar with the muscle inside a charger. Yeah? So the muscle means this is the part who carries the load all the time, and in case of a fault will open and also offers safety in such a charger. And this is the relay, the switching function, an electromechanical relay which we talk today. And I want to get into the requirements which the standards give for such switching functions. I know some of you will say now, oh, standards make me sleep. Yeah? I will try to keep it neat and easy and simple that you are keeping awake. Okay, before we dive deeper, let us first have a look on the forecast for the development of electric vehicles. And here you can see some data actually from Bloomberg, which is still quite conservative. And on the vertical axis, you can see the amount of cars which are sold every year on a global base. And you see we have a value 80 to 100 million cars every year. And on the horizontal axis, you see the timeline. So actually, in 20 years' time, what will happen? And you can see different colored bars. We can see the orange bars, which stand for the internal combustion engine, so the standard car which we have at the moment. Then we have the blue bars, which stand for the plug-in hybrids, which is, as you can see, an interim solutions. Also, that we think this could be only interim. And the green bars represent the pure battery electric vehicles. And actually, the saying of this graphics is that in 20 years' time, half of the sold cars will be battery electrified, and that every year. So this means, if you get the number here, around 50 million cars a year to be sold battery electrified on a global base. And if you can imagine, for sure you need a charging point at home. Yeah, when you go home, you need to charge overnight. But you also need a charging point at work, when you go shopping, when you go fitness. Yeah? So we can estimate up to 1.5 charging points per car, which are needed, and the same amount of relays to be applied on such a charger. So you can see this is a very good outlook that we see also for the relay business. Relay is only a part of the business, but this is the projection, very interesting. And Panasonic is a strong player, offers already since many years, I would say, the highest share in the market with such electromechanical relays for chargers. And today I want to show you also a new development which we have made in this direction. All right, so let's first consider now about charging systems and charging modes, because the standards define different charging modes which we have to distinguish. So here on the right side is the public grid. We have 3 phases and neutral. We come with the car to charge it. In the car we have an onboard charger which converts the AC to DC, and then we go to the battery. And the standards define our mode 4 charging mode. So mode 4, which actually is this fast charging, the high power charger, HPC, which bypass actually the onboard charger because we have DC. So we still have the AC grid, of course, but AC is converted in the charger to DC, and we charge with DC on the car very fast, normally half an hour, and you can charge quite a lot. Then we have the mode 3 charging mode. This is actually the AC charger, so we come from the AC grid, 1-phase or 3-phase system, and we go to the onboard charger, which converts then AC to DC and charges the battery. There's also another mode, mode 2, defined by the standards. This is actually a mode for emergency. So if you're on the way and your battery runs empty, you don't find a charger, or it's broken even out of service, you still can use, or you still can charge your car on a standard household plug, but then you need all the safety and sensoring in the cable. which is then a so-called inline cable control box, where the relay is then in the cable. So mode 2 charger for emergency. So we have to distinguish these modes. And now the question is, which mode has the highest share actually, or which chargers will be sold the most? And here we have some data from McKinsey. First, on the left-hand side, we can see the projection of amount of chargers. So we can see in 2030, we should have around 42 million chargers installed worldwide. On the right-hand side, you see the shares of the different topologies, the different charging modes. And you can see here some AC and DC. So the AC stands for this mode 3, as we said before, and the DC for the mode 4. But for sure, the highest number of chargers we see and we will see in the range of 11 to 22 kilowatt AC charging. Yeah? Three-phase mainly in future, and this is the biggest share in the market. And we offer switching solutions also for DC, but of course AC has a bigger potential also for us. And here we want, of course, to offer also the right solutions. All right, as we are familiar now with the charging modes, let's get to the next question. So why do we need actually a relay, or why do we need to switch in a charger actually? So actually these standards, they define, they give certain definitions what you can do for the safety inside a charger. Because you are connected to the public grid with the charger directly. And as most of applications which are directly connected, they need a safe disconnection from the grid in case of a fault. So safe disconnection means always a galvanic isolation, some clearance on open contacts. So there's no semiconductor to be used here. Only a relay can be used. And you can see here, the standards offer you two options. You have here the installation side in your house, in your building. In the installation, you have also RCDs, residual current devices, which measure a fault current. And if there's a fault current, they will trigger. And trigger means then opening, yeah, of a contact. And there are two options now. The first option, which you can see here, standard says you can use an RCD type B in your installation. Then you are fine actually. Yeah, you don't need anything to care about. You can use a charger even without a relay inside. Or use the other option, which is an RCD type A, but then you need also to include some more sensoring into this charger, plus a switching function, which is then the relay. And we see clearly the trend here that type A is favorized because it's much cheaper than to use a type B. So we talk here about a factor about 10. Yeah? The RCD type B is 10 times more expensive than RCD type A. And type A, most of the installations have already implemented in the buildings. So the trend goes to type A, but what is the problem with type A? Type A actually is blind for very small DC fault currents. So, and the standard defines 6 milliamps. You need to sense 6 milliamp DC faults, so short circuit to ground mainly. And if this happens, you need to deactivate the relay to open the contact and to have a safe disconnection from your system to the grid. So, and this is what is used. So you need a fast sensor. So there are many on the markets, a good sensor for 6 milliamp in combination with our relay to fulfill the requirements of the standard on this one. A sip of water. All right. Now let us have a look on the landscape for the standards for chargers. See, this is from Dipl source, quite nice illustration which we see here. So you see there are many standards which you can use for charging systems, starting really from cables to the connectors, to the plugs, to the communication, many standards here. But for us, or for the switching function, most interesting is the standards which are highlighted here, which is first the IEC 61851-1, which is since many years the general standard for cable-bound charging, which defines all the safety requirements for such applications. But And in this standard, in this general standard, there are different charging modes also mentioned, which we said before. But now there's also a new standard published, the IEC 62955, which is the first standard for mode-free chargers only. So for the AC charging, 1 to 3 phase. And what do the standards define for a switching function? So of course I cannot go now into the standards in detail, also due to the timing. This can only give you really a first insight to the topic. But anyway, we check the standards, of course, and we are also a part of the committees in the standard. And the main requirements which we see are summarized here. So first of all, of course, a safe disconnection is required. So the standards clearly say you need a safe disconnection, and this means mainly minimum 3 millimeter contact gap. And again, no semiconductor can offer such galvanic isolation, so only a relay or a contactor even can be used here. Furthermore, the standards also define some values for the short circuit capability of a relay and the overload. Because you can imagine you are connected to the grid, there can be problems with high currents, with high short circuits also, in both directions actually. So the relay has to withstand it. So to withstand short circuits when it's closed, and also some overload switching are requested. So we have different requirements how to certify such a relay. One other requirement, we need to carry high currents for a long time. So if we talk about the 22 kilowatt charger, each phase draws 32 amps. 32 amps for 3 phases plus neutral. And this, if you can imagine, overnight, if you charge your car in the garage, 7-8 hours, you need to carry this load all the time. Maybe even at a high ambient temperature. So you cannot use from the shelf relays to do this. So this is special designs to fulfill these requirements. Another requirement is the inrush current capability. So when the contact is switching on, you can have also some capacitances in the applications. And here you can for a short time have also a high inrush current, and this has to be withstood by the relay. And one very important requirement, here the last one, is the monitoring of contacts. So the standard defines, it says you need any mean to check if when a contact is welded. So when it's welded and it's not opening anymore. You can do this by different means, by electronics, but we offer also a very nice and elegant solution with our feedback contact, which I will show in a minute. So a feedback contact, we have the welding monitoring inside the relay already implemented. Don't need to take care about it on the electronic side. Okay, then let us have a look on an example of such a relay, and this is from Panasonic actually, the HES relay. The HES relay, as I said before, this is the most interesting part for EV chargers, the highest share in the market. We sell it since 2014 or 15 in this market, and actually we're replacing contactors. So in the past, chargers use a lot of contactors, a lot of DIN rail devices. But as we see now this boom, and we need to have much more chargers in the field. So when you go up to high potential and high volumes, you cannot use a DIN rail contactor anymore, where you have still to screw the cable on. So everybody's moving to the PC board. So in our relays, we offer the PC board relays, which can be automated, mounted and automated soldered for high volume productions. And here you see some data of this relay. So as we said before, the requirements of the standard, and here is actually what the relay can offer. We see also the contact gap, 3.2 millimeter. We have a safe disconnection. We offer 2 contacts per relay. 1B, this is the feedback contact, which is on the left side of this relay, the illustration here. So we have a direct mechanical link of the main contacts to the feedback contact to check if there's a welding. Furthermore, this relay offers the lowest holding power in the market. So for 2 contacts, each contact can handle even up to 35 amps. We offer a coil holding power of only 170 milliwatt, which offers first energy consumption, to have a low energy consumption, but also not to heat up the system without any need. Because the charger gets more and more compact and smaller, you have to take care also about thermal management. So this part is not allowed to emit too much heat. And also, of course, isolation is also requested by the standard, the isolation between input and output side, the 8 millimeter, which is also a reinforced insulation on this. On the bottom, you can see also we have special types as well of this relay, where we increase the shock values, especially for the use in these charging cables, which I showed before, the Mode 2 chargers, where you have the switching function in the cable. Of course, the cable which you put in your trunk, also the customer, we can let it fall, and then we need a high shock value on these relays, which are some special parts which you offer to the market. So Mode 3 AC chargers plus Mode 2, the cables. We offer the HES since years with very good experience and a lot of relays sold, I can tell you. And so this experience help us also now to go on and with the new designs as well on this one. So I want to give you now one more slide, especially on the thermal issue. As I said, mentioned before, so the heating up of this component must be as low as possible to realize very compact chargers. And I want to give you some values of the HES relay, with the relay which we see now. So just to make you see what we have to consider. So first of all, we have to consider, of course, the contact side. Contact side, we have a certain contact resistance. And you can see on the bottom left, this is the distribution of the contact resistance of this relay. And we have such a mean value of 2.2 milliohm about. And if you take this value and calculate what is the power loss on the contacts, plus the power loss on the coil, we end up below 7 watts. Below 7 watts for a 22 kilowatt charger. So this is a very low value, much lower than any contactor can offer. So we see a lot of advantages compared to the contactors in the past to relays nowadays. It's the size, it's the automatic soldering process, it's the low heat dissipation, and it's also pricing actually. Yeah? So this offers completely new features which help it to realize far more compact chargers and also to reduce the pricing actually also on such chargers. All right. Now I want to also give you an example how a new standard is influencing the design also of a new relay. As I mentioned before, there's a new standard that was published in 2018, which is the first standard for Mode 3 chargers, for the AC chargers, IEC 62955. Actually, they increased the requirements quite a lot for the chargers, although from my point of view, there was no need. We don't have any burning in the field or problems with the relays really. But anyway, we have to deal with this standard, of course. And there were two main issues which were increased for the relay. First of all, this standard introduced now mechanical coupling of contacts. This means if you have a three-phase system, 3 phases plus neutral, you need 4 contacts, which have now to be mechanically linked to one mechanism. So before we had 2 HES relays to offer here, but now we need one mechanism, which is a contactor actually, normally. And secondly, they also increased the requirements on the short circuit current. Here is the table 16 from this new standard, and actually the red marked values, this is what we defined with our customers, that we need to survive these values without the welding of contact, which is also very harsh and tough requirement for a relay. This is also especially for a contactor, which can handle it. But we want to get away from contactor, as we said before. And we thought then, of course, we have the HES relay in our portfolio, why don't we do a 4-pole relay on this one, because we need mechanical coupling. But we saw that with this system here, we cannot survive on the short circuits actually, the new requirements on the higher short circuits. So we had to do a completely new design of a relay. So with our Japanese colleagues, our design team is in Japan, where we realized actually the first PC board relay on the market to fulfill the new requirements. And here you can have a glimpse of it. This is actually called the HER relay, which has also the short circuits certified in the VD certificate of this relay. And maybe I will also only give you an imagination of the sizes here of a relay. Here's the HES relay with 2-pole, and now we have a 4-pole relay, the HER relay, which is the new one for the new standard, which is a very good market response to follow this new standard. And of course, everybody wants to have state-of-the-art design and to follow the new standard. So we are ready for this. We made the right component, and will also, of course, continue to do this. We will follow up on the standards. But this is a good example actually to see that also new standards can push innovation and a new design of a relay. Okay, in the end, I have only 2 minutes left. I want also to guide you to our flyer for EV. So the relay set was the muscle, yeah, inside the charger, but we have also something for the brains and the nerves. So communication, and you see also some chokes, power chokes, and many more things to offer. So here's a link you can have a look at if you're interested. Please contact us anytime when we can help you. And one last slide, actually, I want to invite you to the next eMonday in October, 18th of October, where my colleague, Mr. Pascal Meyer, will talk about connectivities, wireless modules from Panasonic to help with the communication inside chargers. Okay, so I hope this gives you an overview now for the moment about the requirements of the standard. And yeah, we are always at your service. Thank you very much for your attention.